So about 2 years after Rutherford's model for the atom, Bohr published a refinement of that model. And it's sometimes called the Rutherford-Bohr model, but typically, to keep the two straight, the first one is called Rutherford, the second one that we're looking at now is called Bohr. Now, the Bohr model of the atom is a planet-like model, and it's going to explain the quantized nature of photon energies by setting things up like this. We're going to have a nucleus with all the positive charge in the center, just like we figured out after we got past the plum pudding model. We're going to have a series of different radii, and in each of those we're going to have an orbit. And yes, it does go to higher levels than this. We're just showing 1, 2, and 3 in this example. Now, you see here that my electron is in orbit number 3. And we've also got an empty orbit 1 and 2. You might predict that it should be able to fall from orbit number 3, where it's high in energy, down toward this positive charge to orbit number 1, and that's going to be something that could happen. But there's a couple of rules that he determined that go alongside of this model. So the first one is that these orbits exist, and there's only certain ones that are there, which helps explain why we can't have white light coming off of hydrogen. Since there's only certain orbits, it has to transition between certain energies. And those transitions are going to be very specific, which means you can't get white light. You only get the fingerprint colors off of the atom, just like we predicted. Now, as long as we stay in the same orbit, there's no release of energy. Now, I'll point out that that could be something a little funky, because as the electron's moving around, we should end up seeing some other features happen out there in the universe. There could be magnetic fields or other electrical fields or something like that that would cause inductions in other things. That's way off the map for where we're at. But it is something that some clever people pointed out after this and said, you know, we're still not quite sure about that model. This model is going to need some refinement as well. But that's one of the postulates of this. There's no radiation of energy within the same orbit. Now, that's certainly going to be true at the level we're going to look at it as far as light goes, but we'll add some refinements into that here in a little bit. Now, whenever we do have movement between two radii, or two orbits, that's going to have a change in energy associated with it. And if we have a change in energy, that energy will be in the photon. And the photon's energy will be the difference between the two different positions. And just like we've seen before, E equals h nu. So energy is proportional to frequency. And then from there you can convert that into nanometers in form of wavelength. Now notice, we can go from high to low. We can also go from low to high. That would have a different sign associated with it. We usually don't care about the sign of it. One example of that would be a $5 bill is worth $5. It's got a negative sign associated with it for me when I give it to you. You have a positive sign associated with receiving the $5 bill. But how much energy is inside of this photon? The $5 bill? $5. Doesn't need a sign associated with it. That's how we handle this. So you can kind of ignore the fact that there's going to be a sign if you switch around the order of these, for our purposes at least. But what the sign does tell you is whether or not the photon is being emitted or absorbed. Notice if we go from high to low, we're taking a high energy and going to a low. Energy is neither created nor destroyed. So if we have high become low, the extra energy had to go somewhere. That means a photon gets emitted. If we do the opposite, we go from low to high, we have to put energy in. Just like picking a book up off of the table. We have to put energy in to lift that book. So for this, we'd have to put a photon of light in, and we'll often just write a photon as being h nu. The energy of the photon equals h nu, so you'll see that I end up sliding into that notation fairly often. Not something to memorize, but something to recognize. Okay, so 3 postulates so far. There's only certain allowable orbits, no change in energy when it stays in the same orbit, and if I change orbits, that's got to be associated with a photon. Now, if I look at the hydrogen atom, and I start out, well, and I do everything, let's not use the word start out. If I do everything involving the second level, then I end up having these transitions. A small transition is a small amount of energy. So that's going to be the red end. A larger photon of energy can allow me to jump 2 levels. If I emit even more energy, that's because it dropped for 3 levels. Even more energy is when I drop 4 levels. And hey, look at that staggered approach. If we have the rings spaced out the right way, that actually starts to explain those neat little repeated patterns that we saw in our line spectra. If we look at the Paschen series, that's going to be when we have n equals 3 starting. So if we're dropping down into n equals 3 from higher levels, we'll end up having infrared. Now I'll point out, infrared is lower energy than red. What a surprise! We're starting from out here and we're dropping to one that's even further out, so it's a smaller transition. The small transitions, small energy, infrared. The bigger transitions are going further in. Those are visible. These ones go even further in, ultraviolet. And so for those emissions, we're going to see photons coming out. I'll also point out we could turn this around and shine those lights in to a relaxed atom where the electrons are all on the inside and pull them out to those orbits. Now, if we were to plot them out and put energy on a coordinate, notice we're in joules of energy per atom, and we're multiplying it so that it's actually something we can see. These are really minuscule amounts of energy when we're talking about a single photon. Now, if I'm starting way out here, if the radius is infinity, that means the electron is someplace out in the universe. And pulling it in from someplace out in the universe will get some size. Now, of course, there's going to be a whole bunch of different radii that could be that far out, right? And remember what we were seeing with the line spectra is that we start getting closely spaced lines packed in right in here. This is from these lines right here, from all these extra levels that we're just not drawing in there for clarity's sake. Starting with 6, 5, 4, and 3, you can see that we're dropping down and getting these energies out for the photons. With the Lyman series, since we're dropping all the way in to the inside layer, that's going to be ultraviolet. That's going to be our high energy. For the visible, we're only dropping down to n equals 2. For the infrared, we're only dropping down to n equals 1. And notice that since we're still using some of these same levels, that explains why we had that similar looking sort of pattern about how far spaced they were on our wavelength scale. Now, here's another neat thing they realized is if they massage the numbers for hydrogen neutral atom only, in other words, 1 proton in the middle, 1 electron zipping around outside of it, not 2 electrons, not 0 electrons, not neutrons there too, not 2 protons, which would be helium. As long as it was only 1 proton and 1 electron, this equation was true. Now, that's a pretty narrow set of circumstances, but it really let them figure out what was going on. I point out how narrow those circumstances are to say, I'm not insisting that you have the Rydberg equation memorized. And that's this equation you see here. You'll do problems with it. I want you to recognize what it's telling you and the importance of it, but I'm not going to insist that you write this as some sort of a trivia question. Now, they also didn't know exactly what this factor was going to be. You can find some deeper meaning to the Rydberg constant, maybe, but we're not going to focus on that for our course. That's a section of the map labeled Here Be Dragons. For the Rydberg constant, if we put this multiplier in, if we put in our levels and we subtract them, we get this value out. If we take the inverse of that, we actually find out the wavelength that we should expect. And I can do that by plugging in, for example, n equals 3 to n equals 2. If I plug those in, I'd have n equals 3 to 2. I'll square them both, so that'd be 1/9 minus, let's see, 1/4. I get a negative value for that. I take it times here. That would tell me that it's a negative change in energy. So that would be something where I'm emitting a photon, going from level 3 to level 2. If I reverse that, I'd end up having a positive value, and I'd be going from level 2 to level 3. We're not going to beat that to death in the lecture. You'll probably try that with a problem just to make sure that you understand what the math tells you, though. Beyond that, we're not going to have it memorized. We're just going to work with it. Now, One of the other neat things about the Rydberg equation is that it was determined experimentally. In other words, they didn't come up with the theory for that equation. They just took a bunch of numbers, plugged it in, massaged the numbers until they found a system that worked, and then published it. That's a funky way to do science, and it's one of those ones that makes us cringe as scientists today, but that was a really clever thing that they did, and they were able to get the behavior figured out from that. But I really want to emphasize, this only works if there's one electron present. The moment you've got 2 or 3 or 4 electrons, things get very, 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 very complicated. That's when you start using a supercomputing cluster and start making very dramatic assumptions or simplifications. The math can no longer be solved exactly.